Okay, so now our next lab exercise 6, and what we're doing here is we're creating a normally distributed population with a mean of 50 and standard deviation 10. We're making 100,000 draws for this, and then we're going to draw increasingly larger samples from this bigger population and see what happens to the mean and standard deviation. So I'm going to try and type a little softer this time because it was a bit loud in the last video. But for pop_n, we're storing the variable pop_n random numbers from normal distribution, 100,000 draws, mean of 50, standard deviation of 10. So that created a set of numbers. And now we're just going to draw one person from them. Sample 1, which is a sample of pop_n. So this time we get mean of 39 and standard deviation of NA, or not applicable, not available kind of thing. It says that because there's just one number and there's no way to calculate a standard deviation with one number because there's nothing to compare that first number to. And so we get this mean of 39, which is really far off from the population mean of 50. Try and draw 3 people. Oh wow, well, 50 already. I didn't want to be that good. Okay, so I'm just doing it again. Now we have 52 with a standard deviation of 6. Which is still not the standard. So anyway, you do 10 draws. 52 again. 25 and 100 draws together. 51 and 48, so the sample mean is pretty close to the population. Yeah. And 1,000 we're just 0.11 off. Anyway, what you should be seeing is that as the sample size goes up, the standard deviation should go down. It should plateau kind of quickly, maybe around 20 or 30 people. Your sample should start approximating the population it's representing, and the mean should obviously go close to the population mean. And the reason is that if you're drawing really tiny samples, they could come from anywhere, from the tail or somewhere far from the center, like any spot in the distribution. So it's more likely we would have a couple extreme values, which would throw everything out of whack and end up with a really large standard deviation. But if we're taking a lot of draws, then since it's much more likely to have average numbers, the greater proportion of numbers being more average numbers would make things more representative. So like see, we get 17, 6, 7, 11, 13. And they're doing 100, 11, 10, 11, 9, 10, 9, 10. See, you don't have those random spikes you do with the other group. So now part B, we're taking a small sample of 20 people from the group we created in A, and we're going to say we gave them some kind of training which raised their mean by 8 points. And we want to see how likely is it we will find we could just randomly sample from that larger group a sample with a mean larger than the one thanks to the treatment. And it's extremely likely that we could sample a number that big or larger, then it's very difficult to say the treatment had any effect. And if it's extremely unlikely that we'd randomly draw a group that performed that well, then we can say theres likely to be an effect. So we're going to create a new sample. I'm going to sample from pop_n again, 20 people. And we're going to store in the variable m1 the mean of new sample. that is 47. Okay, let's just, whatever this is, let's do 49. Sure, okay, fine. Okay, so, and what we're going to do here is, oh, okay, I see. Instead of, we're just going to store the mean of the original population plus 8 into a variable called m1 new. So m1 new is 57.4 instead. Now, a different way you could do the same thing actually is instead, let's say we stored it to m1 new. We stored new sample plus 8. And now we store it to m1 new the mean of m1 new. So it's just getting the mean of this number and racing at whatever was in that and putting the mean of that sample in. M1 new. You also have 57. So basically, what that was doing when I did new sample plus 8, it was just adding to new sample 8 into every single value. So I just thought I'd show you another way to play with the numbers rather than just increasing the mean that we had, actually adding to the values. Anyway, let's move on. We're going to get the z-score for m1 new. M1 new subtract from the general population divided by the standard deviation, which is divided by the square root of length of new sample. And as I said before, length is just the number of things, the number of numbers stored in that variable, which would be 20. So we wanted to get a z-score. We get a z of 3.3. Now you should remember that's a pretty high z-score, which is confirmed when we try to get the p-value of this, and it's 0.0004. So like 0.04% chance of getting a number that big or larger drawn randomly. So the treatment, which in this case was just me putting in plus 8, but yeah, the treatment for whatever this group is did seem to be effective. That should be all for